Welcome to BKW Physics. I'm Mr. McConley, and today we're going to talk about circular motion. And I want you to think of basically anything that travels in a circle. We'll start with the old amusement park ride, the rotor, where it spins around and you get pinned up against the wall, and you usually feel like vomiting by the end of the ride, but that's a whole different thing. But you're spinning around and you're getting stuck against the wall, and that concept is going to play into what we're learning about right now. So if I take an object, in this case, let's pretend you're standing in the middle here and you're holding a long rope, and on the end of the rope you have a rock. And that rock, you're spinning around and around in a circle, just like that. You're spinning it around and around. Let's say it's going this way around the circle for this particular picture. So as you're spinning that rock around and around and around, if that string were to break at any given moment, where's the rock going? So if the string broke right there, or the string slips out of my hand, so all of a sudden I let go, where's the rock going? A lot of people are pointing. Basically, it's going to go this way. And in physics, or in math, we call that tangent. Tangent to the circle at that point. So, when you're talking about something spinning in a circle, and you want to state the direction of the velocity, you say that the velocity is always tangent to the circle at that point. So tangent to circle at that point. So wherever we are, if I'm over here a moment later and that string breaks, it's going this way. That is the direction of the velocity, tangent to the circle. Okay, check that off. We got velocity. But there's other things at play, because it's not just the velocity. What do you feel when you're on that ride and you get pinned against the wall? It's like someone is physically pushing you against the wall, but there's no one pushing you. You feel, probably because of inertia, because your body wants to keep going straight. But there must be something preventing you from going straight, which is actually the wall of the ride, right? The thing that's behind you, because your body wants to just like go like this way and go sideways that way, but the wall is like pulling you in a circle. Another example would be, okay, if this is the Earth, and this is a moon or a satellite, doesn't really matter what it is, this moon or the satellite is going around the Earth. What is keeping it from flying away? In this case, the force of gravity. Thank you. Good answer. So the force of gravity is constantly pulling you in. So if the moon's here now, the force of gravity pulls you in this way. If the moon's here, the force of gravity pulls... Is it the same with this picture? What's doing the pulling? Is it gravity? No. It's a string. It's a string. So in this case, if the rock is here, there is a force that is pulling inward. And if the rock is here, there's a force pulling inward. And if the rock is here, there's a force pulling inward. That specific force has a specific name. It's called centripetal force. Put a little lowercase c. So this Fc is the centripetal force. And I'm trying to say it real clearly because there's this other thing, centrifugal. No, that's not even a real physics thing. Okay? Centripetal means center-seeking. Center-seeking. That's the physics one. Center-seeking force. Something that is towards the middle of the circle. Center-seeking, centripetal force. But Newton's second law, let's go way back in our memory banks. What did Newton's second law say? If there is a force...
Acting on another force.
Second law.
F equals M times A.
That. F equals m times a. It says, Newton's second law says, if you have a force, you're going to have an acceleration. We have a force. We're going to have an acceleration. What direction is the acceleration? What does the rest of his law say about the directions of forces and accelerations? And if you're watching the video, I'm pointing over there because it's written on the wall. And so they're trying to squint, the students are trying to squint to see it. What do you see about the direction?
Would you find out?
It's in the direction of the force.
In the same direction. So if the force is center seeking for a circular thing, then the acceleration must also go the same direction. So you can put a second arrow for our diagram here, which shows AC, that's a lowercase a, by the way, AC, which is centripetal, again, center seeking. Acceleration this time, though. Center seeking acceleration. Now, some of you right there are like, oh, this doesn't make any sense. Especially if I tell you that, let's say the velocity is 5 meters per second. Constant. Constant. It's going 5, it's going 5, it's going 5, it's going 5, it's going 5. How can I be accelerated if I'm going 5, going 5, going 5? Yes. Acceleration depends on two things, remember. There's always two things. You can either be changing your speed, which we're not. That'd be a no for this one. Or you can be changing the direction of your speed. That'd be a yes. You don't have to have both of those to make it true. You just need one of them. So we're changing our direction. We are accelerating because we're changing our direction. And you feel it if you're on this amusement park ride. Instead of being a rock, this is you spinning around and around. You feel it. It almost makes you a little dizzy, and you constantly feel something like pulling you. You're like, and you feel like you're stuck to the wall. Or if you're on like the swing set ride where you're in that little swing and they whip you around and the swing swings out to the side. You've been there, right? You understand what I'm saying? That's centripetal force and centripetal acceleration. Now, let's get to the equations. They're real easy. They really are. First of all, if you want to know how fast you're going, back in the old days, it was distance divided by time. Same is true. But now, what's the distance around a circular thing? The circumference? Yeah, which is 2 pi r. And just to be really technically correct, instead of using the letter t, they usually use a tau, which means the period or the time it takes for one complete rotation. So your equation would be, I'll put a box around it, the velocity is 2 pi r over tau, where tau is the time or the
Bless you.
period of one revolution. Okay, r being the radius, of course, of the circle. Okay, so that's velocity. If you want to know how fast, you do distance divided by time. Boom, great. Moving on to the next thing about acceleration. If you want to know what your centripetal acceleration is, it's equal to your velocity squared divided by the radius. This is new. You've never seen that equation or anything even really looking like it before. It's a new. It's just for circles. So when you're going in a circle, it's v squared over r. V squared over r. And finally, if you want to know the force, start with F equals ma. But this time, just substitute the a that we just learned about in here. So F is equal to m, but instead of a, you put v squared over r. And I'm going to put a little c next to this one also. The c, of course, just means centripetal. Masses are always in what units? No, that's forces. This would be in newtons. This is force in newtons. This is mass in kilograms. Velocity is in meters per second. Radius is in meters. Okay. And that takes care of the main equations for centripetal forces, centripetal acceleration. They're not terribly hard, these problems, but I love the demonstrations. So let's swing over this way just a tad. Can you see me here?
Yes.
Okay. And I have, you might not be able to see, you might be able to see a bucket of water. It's about a third full with water. And you've probably seen this demonstration before, but it never gets boring. It's kind of a fun demonstration where you can go like this, and you can spin it around, and then,
I felt like that. It's
Yeah.
splashing too much.
yeah, it did sound like I was going to lose it, but I didn't. I didn't lose any water.
You lost it.
Why did the water stay there? To correspond with what we just learned?
Centripetal force.
The force, the centripetal force, would be towards the center. That seems like it would pull the water right out. But no. What was providing the centripetal force was the bottom of the bucket. So the bottom of the bucket was pushing in, was pushing in, was pushing in. Which way did the water really want to go? The water really wants to go out, or basically tangent. Back to our picture, the water wants to follow the direction of the velocity. Notice the blue arrow? That's the way the water wants to go. But the bucket makes it curve around the corner by providing a centripetal force. Make sense? Now we're going to step it up a notch, and this one always has the chance for disaster. And I'm using the spill knot from the spillknot.com product here. Nice demonstration device where this is a glass beaker of water. So like I said, there's a chance I could really mess this up, because if I mess this up, it's going to shatter glass all over. And I got some water in that. What I'm really scared of, I don't want to hit the projector on the ceiling when I spin. I'm pretty tall, and I know I can reach the ceiling. So we get this thing going here, and around we go. All right? And I just got to keep the speed even, and then slow it right down, and I'm good to go. So, and you notice the water, actually, the beauty of this, can you see the water? It's not even tipping side to side. Where is the, remember we learned about center of mass of things? Where do you think the center of mass of this device is?
Where the handle is.
Yeah, it's where the handle is, but down here, because this is where most of the mass is actually in the bottom of the water. So it's below the handle, but it's down here. And because of that, it just makes it so easy to balance. It's really actually kind of hard to spill it if you're just walking around with this. You can wiggle it like crazy and the water doesn't even really shake. And because of that, then it makes the demonstration that we were just doing very easy, because what is providing the centripetal force? The bottom of this. Where does the water and the glass want to go?
Tangent.
Tangent. It all works out, though, that the one keeps it pushing towards the middle, and you can spin it around in a circle. So for today, that's centripetal force, physics.